The topic of this video is stoichiometry of gaseous substances, mixtures, and reactions. The learning objectives are on the screen, so go ahead and pause the video now and write those down. So to address the first learning objective, which is to use the ideal gas law to compute gas densities in molar masses, I'm going to start there, and then we'll do a quick practice problem and then proceed. So recall that the ideal gas law is PV equals nRT. Kind of just rolls off the tongue. And so what we can do here is also contemplate what is the definition of density, which is mass over volume, right? Grams per milliliter is a common form of density that we've encountered for liquids before. And so it's mass over volume. And so what this indicates is that we can actually use the ideal gas law to express the density of a gas using things like pressure and the ideal gas constant, temperature, and mole amount, for example. And I left out volume because volume is the key variable that links these two equations. So what that means is if we solve the ideal gas law for volume, volume equals nRT over P, what we can do is then we can also substitute that volume in for the volume for density for a gas. And what we end up with is something that looks like this. Density of a gas is equal to the mass of the gas, lowercase m, multiplied by the pressure, divided by the mole amount of the gas, multiplied by the ideal gas constant, multiplied by temperature in Kelvin. So what we can do is we can also separate out the mass over the mole amount, something like grams per mole. If we think about that as its own term, multiplied by pressure over RT, P over RT, this m over n, it's really just grams per mole. Those are the units here. And those are the units of molar mass, right? So this is also defined as molar mass. So you can see how if we merge density with the ideal gas law, we can get molar mass. Density is specific to a gas. Okay, so this is where now we're modifying the ideal gas law, making it turning it into expressions that are specific to gases. The ideal gas law itself is not specific to any one gas as long as it's applicable to any gas that is an ideal gas. So we can call this capital M kind of italicized. I'm trying to distinguish that from non-italicized capital M, which we use for molarity. So then the key equations here are density equals the molar mass, that's what I'm talking about here, multiplied by, you might want to mark that in your notes. This is the molar mass that we're talking about here, not molarity. And we can also do a rearrangement if we wanted to, but I'm just going to skip ahead to show you that we can also isolate molar mass. Maybe I'll just draw the arrow over here. We can isolate molar mass and express this as a function of the mass of a sample of gas times the ideal gas constant R multiplied by T all over P V. So these are some useful expressions when thinking about calculating using density or molar mass or trying to derive those from given data. So now that we have the ability to use molar mass and density in conjunction with the ideal gas law, we can start to solve some problems that are really interesting, right? It's actually quite powerful to have these relationships. So here's a practice problem. Cyclopropane, a gas once used with oxygen as a general anesthetic, that's kind of scary, is composed of 85.7% carbon and 14.3% hydrogen by mass. Find the empirical formula. Okay, so if 1.56 grams of cyclopropane occupies a volume of 1.00 liters at 0.984 atmospheres and 50 degrees Celsius, what is the molecular formula? This is a lot of information, but we can use some of our skills from prior chapters as well as what we just derived to tackle this. The first is just an empirical formula problem. We've seen that before. So you assume 100 grams total, and that allows you to quickly convert from 85.7% to 85.7 grams of carbon. And then we can use the molar mass of carbon to calculate how many moles here, 7.136 moles. We can do the same thing for hydrogen, and what we will find, grams down here. I'm trying to get ahead of myself. Grams per 1 mole and that gives us 14.158. If you normalize these two moles, dividing both by 7.136, what you'll see is that we have um, one carbon and two hydrogens for the empirical formula. So the empirical formula is CH2. If you take the molar mass of CH2 as the empirical unit, this is 14.03 grams per empirical unit. Okay, so I'm referring to this in parentheses as the empirical unit. So that's the first part of the problem. We've done that before. That's why I kind of blasted through it. Now we can use the expression that we just derived, which is the molar mass is equal to the mass times R times T over PV. So what we can do is we can actually calculate the molar mass here and compare it to the empirical mass, the 14.03 value. If they're the same, the empirical mass is the actual formula from that we need to that's the final answer. The empirical formula is the molecular formula. If the molar mass is greater, then we need to adjust our formula so that from the empirical to the molecular formula. So everything is given to us here. We have 1.56 grams as the mass. We can use the ideal gas constant. We do have to convert temperature, and we have to, I think that's the only thing we have to convert is temperature. So I'm going to write this all out. So the problem stated 1.56 grams. I'm using the gas constant 0.0821. This is rounded from the one that we used before, liter atmospheres per mole Kelvin. And also the temperature is going to be 50 degrees Celsius plus 273 gives us 323 Kelvin. We cannot leave it in degrees Celsius. The atmosphere pressure is 0.984 atmospheres, and the volume was 1.00 liters. You'll notice here that the atmospheres cancel out, the volume in liters cancels out, the temperature in Kelvin cancels out, but grams and moles are left, and specifically it's grams per mole. So that's good because that's the unit of molar mass, and we calculate 42.0 grams per mole. So clearly that is larger than the empirical mass unit. So what you can do is take 42.0 grams per mole, divide that by 14.03 grams per mole, and what you'll get is 3. So what we have to do is multiply our empirical formula by 3 to get the molecular formula C3H6. So you see, this is a powerful analysis method. The next thing that we're going to talk about is actually gas mixtures, and specifically Dalton's law of partial pressures. And the main concept of the law is that if you have a gas mixture, the total pressure is the sum of all the individual pressures exerted by each individual gas. So you imagine if we had these three gases shown here in their own individual containers at those pressures, if we put them all into one container, the new total pressure is the sum of all of those individual pressures. So mathematically, we express this by saying that the total pressure, P total, is equal to the partial pressure. So we denote partial pressure as a subscript with whatever that gas is, in this case, A, just as a placeholder, plus the partial pressure of B, plus the partial pressure of C, plus the partial pressure of whatever is, oops, this is supposed to be ... whatever is here. And essentially what the generic form is the summation of all partial pressures in the system, so PI. Okay, so again, these are the pressures exerted by each individual gas, okay? Also worth noting is, so how do we, if we have a mixture, how do we denote the partial pressure? If we only know the total pressure, we accomplish that with something called the mole fraction. So it's chi sub A multiplied by P total. So this is sort of like it is the fraction, the mole fraction of the gas over which represents the amount of the gas in moles over the total moles of gases in the mixture. So what does that look like? Chi sub A is actually equal to the moles of A over the total number of moles, okay, just expressed as a fraction. So all of the mole fractions of all the gases in a mixture should add up to 1, okay? So let's maybe look at a quick problem that deals with partial pressure. In the interest of time, I'm only going to do part A of this problem. I'll leave part B to you. A gas mixture is used for anesthesia, contains 2.83 moles of oxygen and 8.41 moles of nitrous oxide. The total pressure of the mixture is 192 kilopascals. So we're going to solve for A. What are the mole fractions of O2 and N2O? And then I'll leave you to do the actually, sorry, I'm not going to do just part A. I'm going to do the calculations for oxygen, so A and B, but just for oxygen, and then you do nitrous oxide following that logic. So for O2, the mole fraction of O2 is going to be equal to moles of O2 over the total moles. So this is going to be equal to 2.83 moles over, and then I'm going to add 2.83 plus 8.41. Those are the mole amounts provided. This gives us 0.252 mole fraction for oxygen. So pretty much what that means is that 25.2% of the total pressure is responsible, is due to oxygen. So the way that we solve that mathematically is we say the partial pressure of O2 is equal to the mole fraction of O2 times the total pressure. And so it should be, again, 25.2%, but so we take 0.252 multiplied by 192 kilopascals, and that gives us 48.4 kilopascals as the partial pressure of oxygen. So you can go ahead and do nitrous oxide on your own. So for some reactions, when you want to isolate a gas, it's generated from an aqueous solution. So if we're trying to measure the pressure of the gases collected above an aqueous solution, we also have to account for the amount of water that's actually also in the gas phase that exerts some type of pressure. The pressure over a liquid is the vapor pressure. So whenever you do calculations collected over water, you have to account for the vapor pressure. We just treat it just like in the Dalton's law of partial pressures. The vapor pressure will be P sub H2O. It is temperature dependent, so there's a table that you can look up. These are values that you will not have to memorize, but you'll see that as the temperature, if we look at vapor pressure of water as a function of temperature, the vapor pressure, as the temperature increases, so too will the vapor pressure increase. So you typically have to look up what the vapor pressure of water is at your given reaction temperature to then accurately account for the partial pressure of water vapor in the total pressure of your isolated gas. Okay, and then the final thing that I want to talk about is reaction of gases. So here I've just copied and pasted the problem itself and the solution. I'm just going to walk through it. The concept here is that this is to deal with the fact that 1 mole of gas, if it's an ideal gas at STP, will occupy 22.4 liters of volume. So what that means is that it doesn't matter what the identity of the gas is. If it's an ideal gas, the volume is indicative of the mole amount, right? There's a direct correlation between volume and mole amount. So what that means is for stoichiometric purposes, you can just use the volume ratio of a given reaction to solve the problem with dimensional analysis. So here it's telling us what volume of O2 gas measured at 25 degrees Celsius and 760 torr is required to react with 2.7 liters of propane measured under the same conditions of temperature and pressure. So actually, you notice this is not even STP necessarily. It's just that we know if it's an ideal gas and it's the same temperature and pressure, then the mole amount is reflected in the volume. So the solution here, actually, you have to write out the balanced equation. It's a combustion reaction. And when it's balanced, we see here, instead of thinking about just mole amounts, you can think directly in units of volume. Instead of 1 mole reacts with 5 moles of oxygen, we can say 1 volume of this gas, C3H8, propane, reacts with 5 volumes of oxygen to produce 3 volumes of carbon dioxide and 4 volumes of water vapor. Even though it says liquid there. What we can say here then is if you wanted to solve for the volume of oxygen, starting from 2.7 liters of propane, you do not have to go through mole amount because that's kind of a redundant thing. The volume is indicative of the mole amount and vice versa for ideal gases. So what you do is you start with the liter quantity for propane, and you use the balanced chemical reaction to say that for every 1 liter of propane that reacts, it will consume 5 liters of or 5 volumes of oxygen. So here we're sticking with units of liters because that's the starting point, and then that easily allows us to calculate the volume of O2. We did not have to go through moles. It's sort of a shortcut process to compare how many volumes of one gas will react with how many volumes of another gas to produce how many volumes of some other gas.